Hello, everybody. My name is Victor Martinez, and today we're going to be talking about interpolatory quadratures. Let's start with the definition. A quadrature is simply a term, which means the process of determining area. And its formula looks like this. And whenever the most important concept that I want you guys to take out of a quadrature formula, it is that it is a finite sum. And the lambda value, which is this thing right here, are called the weights, and the y value are simply the values of the function evaluated, and they're called nodes. So in order to calculate the integral, the area under this formula, we simply plug it into the integral. And this here is just saying that the values range between a and b, the values that the function can take. So let's start with the general idea. Basically, a polynomial interpolates f in the given nodes if for each value of f, whenever we evaluate it into x, it is also the same when for q, which here we said that f was this complex thing, and we're simply approximating it to a polynomial, which it is very easy to integrate. And then we check if for each point that we choose, it matches completely. If this happens, then we say that the quadrature formulas are interpolatory. All right, let's start with the most basic idea, which is only using two nodes. And we're going to choose A and B in this case. The interpolating polynomial is this, and we can check it pretty quickly, just simply looking at whenever we input A as x, we see that this goes to 0, and this just stays as q of a equals f of a, which is true. So this interpolates. And of course, it happens the same way if we plug in b. So we know that this works. If we input this in the integral, we will be able to calculate the area under the curve. And it is really simple to integrate because most of these values are constants that can be taken out, and it can be divided into two because it is a sum. And whenever we evaluate it, it gives us this, which, as you guys can see, this cancels out. Very simple integral compared to what we have done. So this is called the trapezoidal rule, and it is called that way because it looks like a trapezoid. It's very simple. And as we can see, we've chosen two values, a and b, and whenever one gives us a 0 in this case, it will give us the other one. Very simple. Graphically, it looks like this. All right, now we're gonna try to improve our technique and use three nodes. The first one being the one maybe on the left, then the middle point, and then the other endpoint. Using the same idea, we find out that the interpolating polynomial is this. And we can check it again pretty quickly. If we were to choose x as a, two of this function, meaning this one, two of these polynomials, meaning this one and this one, will go to 0, while this one will remain as 1. So q of a equals f of a, it interpolates. So this is right. Whenever we replace it again into the integral, which is much longer, it will give us this formula, which is called the Simpsons rule. Graphically, it looks like this, and it has the shape of a parabola. All right, so with these ideas, we can define the basic Lagrange polynomials, which basically allow us to divide any number, each interval into each function into many nodes. This can be 5, 6, 200, 10 million. Using the same idea, just let's find polynomials that whenever they get one value, they will evaluate to 1, while all of the other ones will go to 0. So if whenever this happens, they interpolate. Again, we plug it into the integral, we find the area under that curve. And of course, if we have more nodes, the approximation will be better. But of course, this is very hard to do, and using 2 or 3 nodes is most common. But apart from that, the other way that we can, the other approach that we can take to minimize the error is simply subdividing the interval into equally spaced nodes. They do not have to be equal, but let's just talk about them as if they were equal. So it is the same concept. We're going to simply look at each section of the interval, divide it, use the same idea, find an interpolatorily polynomial for that small section, do that for all the sections that we simply choose, and then add them up. This is basically what this is saying. All right. If we were to use this idea, the compound trapezoidal rule, it would simply be this formula, and for the Simpsons rule, it will be this formula. Something peculiar about the Simpsons rule is that the number of nodes has to be even, because we can see that they are like in pairs of three, with the middle one being like the middle of the division. All right, now how does this apply to computers? So we can use what we have, everything that I have explained, to find the interpolatory polynomials and then integrate it to find the area, right? The good thing about computers is that they have a very large computational powers, and they can find pretty quickly numbers that it would take us our whole life. So what we can do is simply find the interpolatory polynomials, which, as we have seen before, it is pretty easy. And instead of focusing on adding a lot of nodes, let's simply divide it into very, very, very small numbers. Usually we chose, very small spaces between them, not numbers. So usually we choose like 6 or 7 or 8 or 12. The computer can do 1 million, 2 million, 3 million pretty easily. So this minimizes the error to almost zero. So using the computational power, it can reach really, really high precision. This is the bibliography I have used, and thank you all for your attention.